All right, today we're going to be talking about statistical significance with sampling distributions. This is a very, well, it might be a long video, but it's a very brief kind of introduction into statistical significance. I want to be very clear, this is not intended for students in a full semester statistics class or an AP statistics class. This is for an Algebra 3-4 statistics unit. So make sure that you're treating it that way, because there are a lot more details that go into this that I'm not going to cover in this video. So we've worked with z-scores in the normal model, so we'll kind of review that a little bit. We've got the weights of African elephants that are approximately normally distributed with a mean of 11,000 pounds and a standard deviation of 900 pounds. So what percentage of adult African elephants weigh less than 9,500 pounds? So we can start, we don't always have to do this part, but I find it helpful for a lot of students. Start by making our normal model, kind of. We have our mean in the middle of 11,000 pounds. My writing is not great because I'm having a case of tendinitis, so you'll have to forgive me. And then we add 900 each time to go up. And subtract 900 each time to go down. Whoops. Okay. So what percentage of adult African elephants weigh less than 9,500 pounds? So 9,500 is going to be somewhere around here. And we want to know what percentage weigh less, so we're looking at everything under this part of the curve out to infinity, negative infinity, I should say. So what we have to do, we can estimate this based on what we know about the 68, 95, and 99.7 rule that we talked about in 9-3. Or we can find it a little bit more precisely, a little bit more closer of an estimate by doing the z-score. So z is the observed value, that would be 9,500 in this case, minus the mean, which is 11,000, divided by the standard deviation, which is 900. When we put that in the calculator, you want to make sure that you put parentheses around the top, or push enter and then divide by 900. And we get a z-score of negative 1.667, which shouldn't be surprising if this is negative, that this is our mean, this is negative 1 z-score, this is negative 2 z-scores, so we would be in between negative 1 and negative 2. Once we find the z-score, to find our percentage, that's the using proper notation, which I don't expect you to do at the Algebra 3-4 level, the probability that z would be less than negative 1.667 equals, I'm going to put that in the calculator, the normal CDF, goodness gracious, normal CDF, all right, I'm making this as complicated as I can. There we go. You find that at the second, you push the second button and then the vars button, which is right below the arrow keys. Scroll down one to normal CDF, and because we want everything in this direction, our lower boundary is negative 99, which is essentially a negative infinity for z-scores. It's kind of an arbitrary number to use for negative infinity, but that's the commonly accepted one. And then we put the z-score of negative 1.667, and we get, finish writing that. We push enter and we get 0.047, and I'll round that to 8. So what that tells me is that approximately 4.8% of adult African elephants weigh, messy writing, less than 9,500 pounds. So that's not a sampling distribution. That's just a simple z-score calculation and using the normal model to make those estimations. We're going to do a very simple, similar thing, but this tells us this is approximately normally distributed. That's not always the case, and so what we're getting into today is sampling distributions, which is how the normal model is used pretty frequently. We did an activity in class, and we used one round as a sample. So everybody flipped a coin. Sample 1, 12 out of 25 students had it land on tails. On the second round, so that was the second sample, 11 out of 25. So we calculated the proportion of tails for each of those 20 samples. And we put all those percentages. This is our 30%, our 30s, 40%, 50%. So these came out a little lower than we'd expect, more in the 40% than the 50%, but we'd expect with a probability of 50% for landing on tails that we'd have a peak somewhere around 50%, and we do. What happens is this is kind of a simulation, very small simulation of a sampling distribution, where we take a whole bunch of samples, each of these flips of 25 coins considered one sample. We take a whole bunch of samples and put them in a single histogram. And what happens is the bigger our sample size is, if we did samples of 100 instead of 25, we would find this comes out as a pretty normal curve. We'd have that unimodal and symmetric. Because when we're taking basically the mean from every sample, they all come out pretty close to what we'd expect to see. And the bigger our sample size is, the closer they become. So a sampling distribution for proportions is created based on what the mean proportion would look like if we took multiple samples of the same size. So basically it's what a histogram would look like if we took the means of lots and lots of samples, like hundreds or thousands of them. And they all come out looking pretty unimodal and symmetric, pretty much like that normal model. And more so if we have a higher sample size. So we need 3 pieces of information. P is the probability of success. Q is the probability of failure. And we're working with data that's only going to have a success and a failure. There's only 2 possible outcomes. So when we're doing this, when we have the probability of success, the probability of failure is 1 minus B. And then N is our sample size. And as I said, the larger the sample size is, the closer to the normal model it starts to look. So there are 3 conditions we need to check to see if we can create a sampling distribution. 1, is it random or reasonably representative? Is the sample big enough? We check that with the success-failure condition. When we do that, we take NP, so N times P, and that needs to be greater than or equal to 10. And we take N times Q, and that needs to be greater than or equal to 10. So we check those 2 things to make sure we have a large enough sample for 10 successes and 10 failures to occur. And then we want to check if the individuals are reasonably independent. Sometimes we can just say, yes, they're independent, but other times we need to check that the sample isn't too large, and that's the 10% condition. This one we pretty often have to assume something about the size of our population, because often we don't know that number. But this says that our sample can't be more than 10% of the population. So cannot be more than 10%. Okay. Again, if this were an AP Stats class, we'd be going a little bit more specific into those things, but since we're not, we're just going to keep moving. So we don't just use the mean and standard deviation. We have to create a model for this. So our mu, that's what this letter is. It sounds like that, mu, is our probability. That's our mean. Is whatever our probability of success is. And the standard deviation, because I couldn't put sigma on there, that's our standard deviation, is the square root of PQ, so it's the probability of success times the probability of failure divided by the sample size. And when you put this in the calculator, you're going to do square root P times Q divided by N. Don't put any parentheses in because that just messes it up. This order of operations takes care of itself in the calculator. Because we're not adding or subtracting anything, it's not an issue. So that creates our sampling distribution. And this is, when we set up that sampling distribution, this is what we think many samples would look like. So let's do an example. It's generally believed that nearsightedness affects about 12% of all children. A school district has registered 170 incoming kindergarten children. Check the conditions and create a sampling distribution for the proportion of kids the school might expect to be nearsighted. So, checking our conditions. Is this random? No, but we can say it's probably reasonably representative. The success failure, we have 170 for our N. Let's write that up there. We got our P is 12% because that's what we think is happening. Q is 1 minus that, so 88%, 0.88. And then our N is 170 because that's our sample size. So 170 times 0.12 equals something. 20.4. Oh, I should have written that that's NP. And NQ equals 170 times 0.88. And this is math you do have to show. The reason I'm making you show this is because if I get you in my AP Stats class, I don't want to have to undo anything that I taught you this year. So I want you to get used to showing those two. This is greater than, both of those numbers are greater than or equal to 10, so our sample size is large enough. And then the 10% condition, presumably we have, if this is a large enough district, we have 170 is less than 10% of all incoming kindergartners. So assuming and we can actually use students, this is just kindergartners, but we can apply this to students, are at least 1,700 kids. this is less than 10%. That may be a big assumption depending on the size of the school. I'm going to shrink that down and draw this sampling distribution. So we have our mean is going to be 0.12. So I'm going to draw, oh, my hand is killing me right now. Middle there is 0.12. And our standard deviation, that's the square root of PQ over N. So square root of 0.12 times 0.88 divided by 170. And you get 0.02, I'm going to round that to 5. So going up, we're going to add 0.025, so 0.12 plus 0.025, 0.145, forgot the decimal, 0.17, 0.195. This is one of those things I can do in my head, and I don't want to get the wrong numbers on a video, so I'm sure it's happened before. 0.095, 0.07, 0.045. So this is what we'd expect most samples to look like. So if we took many samples of 170, we'd expect 68% of them to be between 9.5% and 14.5% nearsighted kids. 95% of them between 7% and 17% nearsighted, and pretty much all of them between 0.045, so 4.5%, and 19.5%. Out here, beyond 2 standard deviations is generally pretty weird. 9% that it's asking about, so what's the probability that less than 9% of incoming kindergarten children are nearsighted? 9% is roughly right here, then I'm looking for the probability that a sample would have less than 9, and we don't really worry about the less than or equal to thing. I know that gets people a little bit hung up, but we're looking at that probability of happening down there. So we go back to what we've learned from the other stuff of the z-score. So z equals 9%, 0.09, minus 12%, our mean, 0.12, divided by our standard deviation of 0.025. When we do that, we get negative 1.2. So this is 1.2 standard deviations below our mean. And then we calculate the normal CDF, the probability that z would be less than that. Again, this notation is not something I would expect you to know, just showing it for future reference if you're taking AP Stats. I put this in as normal CDF. Again, you go to the second VARs menu. Second one down is normal CDF, negative 99 for your negative infinity, and then negative 1.2. And I get 0.115. So basically there's and when I'm looking at this area under the curve, or the proportion of the percentage of samples that would fall below 9%, I'm also looking at the probability that a sample would fall below 9%. So this is a 11.5% probability, or 0.115, not percent, sorry, 0.115 probability that that a sample of 170 would fall below 9% kids that are nearsighted. So when we find that probability, we are kind of basing that on this model that we've created based on what we think is happening. So that brings us to statistical significance, and we're going to do a really, really tiny intro into a hypothesis test for proportions. So Again, we have the same situation. Nearsightedness affects about 12% of all children. A random sample of 250 students in a large city found that 14% were nearsighted. Does this provide evidence that the true proportion of nearsighted children has increased? So we have clearly a sample that's coming out larger than we think it should. It's 14% compared to 12%. So we create a model based on this 12% that we think is happening. And we basically, what we do here is we create a hypothesis. We say this is what we think is happening. So that's not going to be large enough. So what we think is happening, this is our null hypothesis. Is that 12% of kids are nearsighted. That's in words. In AP Stats, you would be expected to do it in symbols. In symbols, that means that our proportion, our true proportion of kids who are nearsighted equals 0.12. And this true proportion thing, this is something that we never truly know, or very rarely know. But it's what we're basing our estimate on. Our alternative hypothesis is based on our sample that we see, and that's that 14%, and we're not saying that it's 14%, we're just saying that we think it's increased. So the percent has increased. So we think that the true proportion, P, has become greater than 0.12. We don't make a guess as to what it really is. We're just saying it's bigger. We also have to check our conditions for this. This stated that it was a random sample. We have to check our success failure condition. Just don't want to write that out. Let's go over to the other side here and write some of the things we know. Our probability of success is a 0.12 because we're basing this model on what we think is going on. It means our probability of failure is 0.88. This time our sample size is 250. So success failure, NP, equals 250 times 0.12, which is 30. And NQ is 250 times 0.88, 220. Those are both greater than or equal to 10, so we're good to go there. And then the 10% condition, this mentions it's a large city, so we can assume that 250 students is less than 10% of all students in the city. So we're good to go there. If this was AP Stats, I would say what test we're going to proceed with, but it's not, and that gets a little too complicated for this. So now we want to go over and create our actual model and do our math. So our mean is that 0.12. This is the same as the sampling distribution stuff. Our sigma, our standard deviation, is the square root of 0.12 times 0.88 divided by our n of 250. This is going to be a little bit different than our last one because our change in the sample size. That's going to make our model a little bit skinnier because our standard deviation is going to be smaller. We're still going to draw it the same though. So 0.12 times 0.88 divided by 250 is 0.02. It's 0.02055. I'm just going to go 0.02 to keep it simple. So I have my model. Oh, God, my hand hurts. Okay, so 0.12 plus 0.02, 0.14, 0.16, 0.18, going down 0.10, 0.08, 0.06. So again, this is saying that of samples of 250, 68% would be between 10 and 14%, 95% would be between 0.08 and 0.16, and almost all of them, 99.7%, would be between 0.06 and 0.18. All right, if I'm labeling this correctly, this would be a proportion of nearsighted kids. Always important to label. Okay, so that's our model. That is based on our null hypothesis that our nearsighted kids are 12%. This is the model we've created. So what we need to do is take this sample at 14% and determine if we think that's consistent with this model or if we think it actually is big enough that it has increased. So we're going to calculate a z-score. So z equals our observed, which was 0.14, minus our mean of 0.12, divided by our standard deviation of 0.02. Which is just 1. So if we think it's increased, then what we're thinking is that we're wanting to find the probability that it would be at 14% or more. So with a z-score of 1, we're going to put that into the normal CDF, so the probability that z would be greater than 1. We do that into the normal CDF. 1 for our lower boundary, because that's right there, to 99, because that's basically our infinity going out that direction. And we get precisely 0.15865, yada, yada, yada. So I'm going to do 15.9%, so 0.159. That number, I'm going to shrink that down, is what is called a p-value. And this gets into some nitty-gritty stuff, again, with AP stats, but the p-value, this probability we get here of this sample coming up here, is the probability of seeing this sample at 14%, given that this model that we've created based on that 12% is right. So if our true mean really is at 12% and we get a sample at 14%, that's not really very shocking. That's a pretty high probability, 15.9 or 16%. Basically, anything greater than 5% or 0.05 for a p-value is generally not considered statistically significant. That's not always the case, but for the sake of this class, we're going to go with 0.05 for that threshold. That statistical significance piece, what that means is that these samples that happen in here, when we're in between 1 and 2 standard deviations, we kind of say that those are pretty likely to happen just by natural sampling variation. All these different samples are going to come up all over the place, but most of them are going to come up between 8% and 16%, maybe a little bit closer in. If we're out between or out at less than 8% or more than 16%, chances are that p-value is going to get a lot smaller. And the further out we get, the less likely it is that this is the correct model. The more likely it is that it's that we would say that we have evidence of the alternative, that it actually has increased. But this doesn't provide any evidence of that. If we have more than a 5% chance of this happening just because, just based on sampling variation, then we don't have any evidence to reject this model. So what we say is we can't reject the null hypothesis. and we don't have evidence. Whoops. So we don't have evidence that proportion has increased. So, what would it look like otherwise? I don't want to do an entire one because this video is getting a little long as it is. But let's say we found one that was at 19%. We would definitely get a really small p-value for that. So what we would say about that is that we do reject the null hypothesis, because this seems so, 19% would be so unlikely to happen if this is the correct model, that we really think that that percent has increased. That's not just from sampling variation. So that's kind of just dipping your toe into sampling distributions and statistical significance. So I hope that helps, and I hope that if that was interesting to you, take AP Stats and you get more into it than this, much more, and you have a lot more background before you get to it. So have a lovely day.